Hi, welcome back. We're talking about observations and the scientific method. The scientific method is integral to this course. And the scientific method is stepwise progression of looking at a problem. So first it's recognizing that there's a phenomena happening that might be associated with the problem. The one I've got in the upper right hand corner are the Australian fires from January of this year that raced through mountains in Australia and decimated their wildlife community, including many kangaroos and many koala bears. Millions were killed. And at the time I was looking at that quite a bit, and I still am looking at that quite a bit because I'm wondering what's going to be happening this coming January in Australia and whether or not the same conditions exist to produce the same result in Australia in January again. So the scientific method looks at a phenomena and recognizes a problem rather than denying it. And it teaches you how to think critically and independently about the phenomena and about the problem. It's a central goal of this course, not to just teach you meteorology, but how to teach you how to think critically and independently about a problem so that you're not going into groupthink or panic. You're looking at something and structuring it so you can have a solution or you can have progress toward a solution. To accomplish the scientific method, we start with, like I said, the observation. Then we go with finding the problem, not just panicking and complaining, but finding the problem. It usually comes with a why question. Why does this happen? And you're very specific about what the this is. Then you go into research about that. Just to backtrack a second, in our COVID problem right now, the very specific questions are many, but one of them could be, why does this impact people who are elderly and obese so much harder than it hits people who are younger and not obese? So you can ask a very specific question rather than getting involved in a lot of emotional feelings that don't get us toward a solution. The research is the next step. And in doing the research, you really can focus your work by looking into scientific laws and theories that are already in place and looking at scientific facts which support the theories, and we'll get into what the difference between laws and theories are, and looking into other scientific hypotheses from other groups that have looked into problems that are similar to the one that you found. This helps to focus your work and save you time and effort. Then you look to bringing in and developing your own hypothesis or your own prediction about a solution. We'll go over that more. And establishing quantitative tests that can measure and test your prediction. You analyze those measures, you make a conclusion about them, and you announce them to your peers in order to try to encourage your peers to better your study and to validate your results. Because when we validate the results, all of those facts lend themselves to new theories. That's the overview. Let's go into the specifics. This overview that I talked to you about goes around in a circle. This circle's been around for thousands of years in some way, shape, or form. And it starts at the top with making observations, then thinking about the questions about why, doing some research, very important, formulating the hypothesis, your prediction about a solution, then devising a method to test those predictions, testing the predictions and gathering the data, analyzing the data, and looking back to see if your original hypothesis, your original prediction, was supported by your test. Maybe it wasn't supported by your test, but that support or that refute is part of the conclusion, and then you announce it to the community so the community can help you and help themselves to better the science and better the data for the better solution. let's go into some more specifics about each step. Before we do that, not only do we avoid sensationalism and we avoid groupthink by using critical and independent thinking methods, we also avoid panic and wasted time and effort. I work in EMS. The scientific method underscores everything we do so that we don't panic, so that we don't waste time and we don't waste effort. We don't waste energy. It's a discipline that you have to practice and practice and practice. That's why they call it medical practice. And in this way, we're going to be practicing all semester to get you better at thinking critically and independently. One sure way to do this is to avoid, one sure way to utilize the scientific method is what we're going through right now with COVID. We could get really wrapped up in quick fixes, or we can do the long-lasting science that it's going to take to meet this problem head on and solve it. And that's what I want to encourage you to do. The specifics of the observations and the problem in the scientific method. This is observing the method. This is observing the issue emotionally in qualitative terms. When people see the dead kangaroos on Kangaroo Island, millions of them, it provokes an emotional observation that's very important to motivate you to continue your work when the work gets tough. So those qualitative observations are very important, especially about weather and about meteorology. Meteorology is a very emotional science. It can devastate your world. And so that motivation keeps people studying when the studying gets really hard. It starts with a qualitative observation, and then you're acknowledging the problem rather than just forgetting that it's in Australia, it doesn't really impact me, and asking a why question. In my case, that why question was, why did the western parkland of Kangaroo Island, look at the western parkland here, it's beautiful green before the fires. The western parkland, which was a beautiful green, obviously pretty well saturated with water, why did that burn so intensely? Why wasn't it quenched by the water that was in the soil? That's very interesting to me. I research and I look for clues to that problem that I've got there. I look through the scientific laws, the theories, the facts, and other people's hypotheses. We're going to get into all the specifics of that in a second. What's the difference between all these laws and theories and facts? Let's go into it. A scientific law is a description of the phenomena, not a qualitative description of the phenomena. A scientific law is a mathematical description of the phenomena. Generally, it's a mathematical description. Some examples include Newton's second law of motion, F equals ma. You know that from high school. Force equals mass times acceleration. And here, the A, like I said there, is gravitational acceleration constant. All right? That's a mathematical description of an apple falling from a tree to the ground and landing right next to Newton. He could describe that mathematically. You are going to be learning in the next few lectures about the ideal gas law, which is pressure times volume equals the number of molecules in a gas times a constant, R, times temperature of that gas. You're going to know PV equals nRT like the back of your hand by the end of the semester. It really determines so much in our atmosphere. The ideal gas law is very important. Again, it's a law that describes a phenomenon mathematically. Now, a theory, what's a theory? A theory is an explanation of the phenomena that you see. And it's an explanation that can be tested. An example, relating back to Newton's second law of motion, the law, the mathematical description, is Einstein's theory of relativity. Einstein explained how gravity impacts mass. He doesn't concentrate on the mathematics in his theory. He concentrates on the explanation of how gravity impacts mass. Now, to explain our ideal gas law that we're going to be concentrating on, we can use the kinetic theory of gases. We can use that theory because that theory explains how particles of gas have elastic collisions, like a pool table, that can conserve kinetic energy. You don't have to write down these laws, you don't have to write down these theories until later. So don't concentrate on that too much now. I want to explain to you what the difference is between a law and a theory. Scientific hypotheses are limited explanations. They are predictions, small predictions about phenomena. They generally include an if this and this and this and this are true statement, then I predict that this and this and this and this will happen. And you are going to be making up hypotheses in this course. If your hypotheses are supported by data, they can in turn support a bigger theory. So it's very important to include new experimentation and new hypotheses and new data, because that data could support the hypothesis and could support an overriding theory. Theories, however, do not become laws, because remember, theories are explanations. Laws are mathematical descriptions. Very different thing. So hypotheses can support a theory. And I'm not going to get, you can read the PDF on this because I don't want to run too long. But facts are actually objective, verifiable observations. Kangaroo Island burned in January 2020. Scientific fact. Okay? Apples fall from trees to the ground. Pumping up a tire increases air pressure by 10%. Fact. All right? To get back to hypotheses, because you're going to be developing them, you look at your research and you come up with your own prediction, big prediction, and then you look back to your research to find specific premises that supported your prediction. Big premises, like in Australia, my big premise is that water extinguishes fire. It's a pretty big premise, right? It doesn't have to be big and specific. I have research that shows me that water quenches fire. Then you get very, very specific about it, and we'll go into it in a second, how that comes about. For instance, my hypothesis here could be, if rain can quench wildfires, yeah. And if oceanic islands have frequent rain, yeah. And if Australia's Kangaroo Island burned uncontrollably, more specific, down the funnel, yeah, it did burn uncontrollably, then Kangaroo Island sustained drier conditions. That's my prediction. I don't know if that's right. That's my prediction. I can test it. The hypothesis is a testable prediction. Thanks, and I will get back to you in the next one more about the scientific method.